Dear students, this is Dr. Pardeep Singh, and today's topic of discussion is point defects. In the previous lecture, I have discussed about the defects and their classification. Now, in this topic, our main focus remains on the point defects. Now, in the point defects, there are two main defects. One is Schottky point defects, and second is Frankel point defects, which found very common in crystal structure. So these defects are always present in a real crystal at finite temperatures in thermal equilibrium. Now let's discuss about the Schottky defects. To derive the expression for Schottky point defect, let us consider a perfect crystal. For example, sodium chloride at temperature T is equal to 0, having equal number of positively, negatively charged ions. Now, vacancies are created due to raising the temperature. As we know, whenever the temperature is raised, there is a possibility to create a vacancy. Now, the equilibrium concentration of vacancies can be found at any temperature. When a positive ion migrates from its position to the exterior of the crystal, a certain vacancy occurs. Now, at the same time, the excess negative charge produced inside the crystal helps the formation of negative vacancies. Now the negative and positive vacancies are same in number. Now to find the expression, we will use the thermodynamical equation, which is F is equal to U minus Ts. Here F is the free energy, use the internal, and S is the entropy of the crystal. Now the total increase in energy due to production of vacancies will be equal to U is equal to NEP. Let it be equation number 2. Now small n is the number of vacancy pairs, and EP is the energy required to take a molecule from the interior to the surface of the crystal. The entropy is given by the Boltzmann statistical relation, that is S is equal to K log W. And we know that this is very famous equation, and this is the link between statistical mechanics and thermodynamics. Now where W is the number of ways the total vibrational energy of the crystal may be distributed, and K is the Boltzmann's constant. Now let capital N be the total number of atoms in a crystal, and small n, the Schottky defects are produced by removing n molecules, that is n cations and n anions. The different ways in which each kind of ion can be picked, that is equal to W is equal to n into n minus 1, n minus 2, up to n minus small n plus 1 divided by n factorial. We got this relation from the concept of probability, which is the probability of picking small n number of ion molecules from the total capital N number of molecules. Now, eventually this expression becomes equal to n factorial over n minus small n factorial into small n factorial. Now considering the ion pair, the each term should be squared. Now as we know that there are two ions, cations and anions, therefore the probability will become the square of this term, that is square of n factorial over n minus small n factorial into small n factorial. Now put the value of W in equation 3 in the previous equation, that is S is equal to K log W. The value of W supplied in this equation, and this equation becomes K log n factorial over n minus n factorial into small n factorial, its whole square. Now this value of S put in equation F is equal to U minus Ts. U is the total internal energy, which will be equal to N into EP. EP is the energy to pick the ion pair from the interior of the crystal, and minus KT log n factorial over n minus small n factorial, then its whole square. Now we know that the Stirling's formula is log x factorial is equal to x log x minus x. Now using this formula, we can find the value of this term, this log term. Now this will become 2 log n factorial minus log n minus n factorial minus log small n factorial. Now by using the Stirling's formula, expand these log terms, and we will get 2 into n log n minus small n log n minus small n minus n log n. Now differentiate this term, differentiate the expression for f. So the differentiation of f will become ep minus 2 kt log n minus n over n. So this is the simple differentiation, and we can differentiate by considering the other terms constant. Now by substituting this value in the upper equation, now we will get f is equal to nep minus kt 2 into n log n minus small n log n minus small n minus n log n. Now differentiate this equation with respect to small n. Now we will get curly f by curly n is equal to ep minus 2 kt log n minus n over n. Now this is simple differentiation. Now when the equilibrium is attained, the free energy will be constant. Therefore, curly f by curly n should be equal to 0. Now put the value of curly f by curly n from the previous equation. Now this will be equal to ep minus 2 kt log n minus small n by n is equal to 0. Now from this equation, find the value of ep. Now ep will be equal to 2 kt log n minus small n by small n. Now divide 2 kt on both sides, then ep by 2 kt will become equal to log n minus small n by n. Now here n minus small n by n can be calculated by taking the anti-logarithm on both sides. Now this equation will become n minus small n by n is equal to e raised to power ep divided by 2 kt. As we know that the number of Schottky defects are very much lesser than the number of atoms, therefore n minus n should be approximately equal to capital N. Now thus the relative density of vacancies is given by small n by n is equal to e raised to power ep divided by 2 kt, or the number of approximate Schottky defects present at any temperature T is given by n small n is equal to capital N into e raised to power minus ep by 2 kt. So this was the expression for Schottky point defects. Now let's discuss about the Frankel defect. Now in the Frankel defect, the atom is transferred from a lattice site to the interstitial site. Therefore, Frankel defect has two parts. First one is the vacancy and the second one is the interstitial site. Now the two components of the Frankel defects are independent of each other. Now let EI be the energy required to displace the atom from the lattice to an interstitial site. N are the number of atoms in the crystal and Ni is the interstitial sites available within the crystal. The number of ways in which n Frankel defects can be formed is given by the equation W is equal to n factorial divided by n minus small n factorial into small n factorial multiplied by ni factorial divided by ni minus n factorial into n factorial. Now the Helmholtz free energy is given by F is equal to U minus Ts, as we discussed in the previous part of this lecture, which is equal to N EI minus KT log n factorial divided by n minus n factorial into ni factorial n minus n factorial into n factorial. Now again, using the Stirling's formula, we get log n factorial over n minus n factorial into n factorial plus log ni factorial over ni minus n factorial into n factorial. It comes out to be n log n plus ni log ni minus n log capital N minus small n minus ni minus small n log ni minus small n minus 2n log n. Now again differentiating this equation, we will get curly f by curly n is equal to ei minus 2 kt log n minus n into ni minus n divided by n square. As we know that at the equilibrium the free energy is constant, and so curly f by curly n is equal to 0. Now again here we have n, and ni is greater than equal to n, so we can neglect, we can put n minus n is equal to n, and ni minus n is equal to ni approximately. So this equation will become ei upon kt is equal to log n into ni over small n square. So finally we get n is equal to n into ni root into e power minus ei upon 2 kt. This is the expression for Frankel defects created in the crystal. So thank you for listening this lecture. Bye bye.